Hey everyone, and welcome to this Forge College Explainer. I am absolutely thrilled you're joining me today because, well, we are diving deep into the architecture of Solana programs. If you've ever wondered how on-chain programs actually talk to one another, you are in the exact right place. We're going to take some pretty complex protocol mechanics and break them down into something so clear and so visual that it's going to permanently upgrade your mental model of how all this works.
Okay, let's dive right into our agenda. We'll be hitting 1. From client to on-chain, 2. Chefs, bowls, and ingredients, 3. How the runtime works, 4. Signers and authority seals, 5. Token transfer and practice, and wrapping up with 6. Review and next steps. All right, Section 1. From client to on-chain, moving beyond the client script. First off, I just got to say a massive congratulations to those of you who just crushed the capstone, assemble, and deliver the client interaction script. You've officially mastered sending instructions from the outside world. Seriously, great job. But now, well, our next challenge is moving those dispatch decisions entirely on-chain. So let's look at a clear definition. A cross-program-invocation, or CPI for short, is basically an on-chain program invoking another program's instruction inside the very same transaction. It passes accounts and instruction data so the callee runs as part of the caller's execution. Now, I know that sounds like a mouthful, but here's the cool part. You're actually just reusing primitives you already know, like account ownership and transactions. But instead of a user talking to a program, we're composing them program to program.
And this visual brilliantly illustrates the shift we're making. In the old way, a client script submits two completely separate instructions to the network, right? But in the new way, program A takes the wheel. It literally asks the runtime internally to execute an instruction in program B. This kind of internal dispatch opens up incredible new opportunities for sharing state and building composable programs. But, as we're going to see, it also introduces some very strict new constraints.
Moving on to Section 2, Chefs, Bowls, and Ingredients, a Web3 kitchen metaphor.
I absolutely love using this Web3 kitchen metaphor because it perfectly grounds all this abstract code into a relatable physical space. Think of the client submitting the transaction as a loud restaurant manager shouting out orders. The programs? Those are our chefs cooking the meals. And the accounts are the bowls of ingredients resting on a shared prep counter. Now, in this shared kitchen, there are 3 absolute non-negotiable rules. First, mutability. Can the chef actually alter the contents of the bowl, or are they just allowed to look at it? Second, signing authority. Some of these bowls are locked tight with tamper-evident seals. A chef literally cannot pretend to have broken a seal with the proper authorization recipe. And third, error atomicity. If a chef drops a bowl and spills the ingredients, boom, it ruins the entire meal service. Everything just stops, and the kitchen forcefully resets to exactly how it looked before cooking even began.
Okay, Section 3. How the runtime works. The strict physics of the kitchen.
So we're transitioning from our fun little kitchen metaphor over to the strict protocol-level mechanics. You can think of the Solana runtime as the uncompromising laws of physics that govern our kitchen. Notice how minimalist this engineering schematic is? When you build a CPI, you are essentially grafting these specific components onto the current transaction execution context. You pass the program ID so the runtime knows exactly where to route the call. You pass the instruction data, which interestingly the runtime completely ignores. It leaves that entirely for the callee to interpret. But that account meta list? Oh man, that is where the runtime acts as a strict bouncer, rigorously enforcing presence, signer, and writable checks.
So, the absolute crucial point is captured right here in this quote. Mechanically, the runtime does not duplicate accounts for the callee. It references the same account structures in memory. There is literally zero automatic isolation. If Chef B, the callee, reaches in and writes to an account, they are altering the exact same physical state that Chef A, the caller, is looking at.
And because they share that exact same physical bowl, those writable flags matter immensely. If a bowl isn't explicitly marked as writable in that account meta list, and the callee tries to modify it, bam, the runtime throws a massive error. If an inner CPI tries to magically elevate read-only access up to writable, the runtime strictly denies it, unless the outer execution frame already allowed it. All right, on to Section 4, Signers and Authority Seals, unlocking the PDAs.
Back in our kitchen, PDAs are kind of like specialized bowls with these mathematically coded hinges. Only a specific program knows the exact combination to pop that hinge open. Let's look at how we actually open them. On the left, we've got external signers. These are your standard user wallets, the original transaction signers mapped directly to the execution frame. But over on the right, we have PDA signers. Because a program obviously doesn't have a private key sitting on a hard drive somewhere, it has to sign via a seed-derived signer mechanism. Remember, if a signer flag is missing, it cannot be magically elevated by an inner CPI. Your rights are strictly, fundamentally constrained by what was presented.
And I really want you to burn this number into your memory, 1. This represents the single execution frame. You see, the runtime implements a strict stack-like model. If the callee throws an error, the runtime immediately unwinds that specific frame. It rolls back all the writes that just happened, and typically, it aborts the entire transaction outright, unless you've intentionally and very carefully handled that failure in your code. Like we said earlier, spilling the bowl ruins the meal.
Section 5. Token transfer in practice. A concrete example with program A and B.
Let's ground all of this by having program A move some tokens using program B's transfer instruction. Here's the exact step-by-step sequence. First up, we set up our mint, our source token account, T, which happens to be a PDA, and our destination, D. Second, program A prepares the CPI, making absolutely sure to mark both T and D as writable since, balances are going to change. Third, and this is vital, program A calls the instruction using PDA seeds because it can't provide an external signature. Finally, program B either executes the transfer or, if anything at all is wrong, it rolls the whole thing back.
I want to highlight step 3 just a bit more. Invoke_signed is the specific program-level API required to tell the Solana runtime to treat a PDA as a signed account. If you, as the developer, accidentally use the regular invoke method and forget the signed variant, the token program is going to look at the account, see a non-signer, and instantly return an access error. No tokens for you.
Finally, Section 6. Review and next steps. 3 practical habits. We have covered a ton of ground today, but applying it is where the real magic happens. So every single time you sit down to write a CPI, I want you to stop and ask yourself this exact question. Which bowls go to the callee, which must be writable, and which needs signed access? I want you to really cement this mental framework. It's going to guide exactly how you configure your account lists every single time.
To successfully answer that question, you need to adopt these 3 practical habits right now. Number 1, assemble your account metas intentionally. And remember that for some programs, positional order actually matters. Number 2, always run your local precondition checks before invoking an external program. This simple step saves you from so many costly runtime errors. And number 3, design your control flow for safe imponent side effects. Trust me, these 3 habits are going to save you massive headaches when you're trying to debug nested invocation stacks later on.
Up next in this module, we'll get our hands dirty with CPI configuration and state sharing, where we translate all these mechanics into actual working code templates. Thank you so much for watching this Forge College Explainer. To master more Web3 topics and continue your programming journey, be sure to visit us at Forge College. But before you go, I want you to think about this. In the programs you are writing today, are your digital bowls properly sealed, or are you accidentally leaving your ingredients wide open for anyone to spill? Keep building, and I'll catch you in the next one.